Hello and welcome to a deep look into No Man's Sky's logic system. Now, No Man's Sky has 5 switches, and these 5 switches work basically the same. Every switch has has 2 input-output connections, and the switch itself can have 2 states, an open state and a closed state. When the switch is open, the signal, this is the blue one, can flow through the switch and come out on the other end. When the switch is closed, the current is the signal is blocked in the switch. So the functionality of the button switch is when we press the button for a short moment of time, the switch will open, allow the signal to go through, and then close again, as we can see here. The second switch is our wall switch. The wall switch has a permanent state. It can be permanently open or permanently closed. When we open the gate, the switch, the signal can go through the switch and switch the light on. And we can close it manually, but we have to do this manually. The proximity switch works a bit different. It basically measures your distance to the switch. So if you're within a distance of about 1 meter, the switch opens and allows the signal to go through. And in order to close the switch again, you have to go away around 2 meters. The other 2 switches are more interesting because they work automatically. Now, also these 2 switches work in the same principle as the first 3. We have 2 input-output connections where a signal can go through, and we have a third input, which is a control input, and this control input will control whether the switch is open or closed. So the difference between the inverter and the automatic switch is that the automatic switch will be open as long as there's a signal on the control input and closed otherwise. The inverted switch will be closed when there's a current and open otherwise, when there's a signal on the control input, and open otherwise. So we can see this here. We have I have 2 examples, and we have no signal here on the input, and we have a signal here on the input. Both control inputs are off, and in both cases we have no output, or we have a 0 output, as we say. And now if I toggle the control input, we'll see that the switch has opened, which means since here is we have no signal here on one side, we also have no signal on the other side. But since we have a signal here coming into the input and the switch is opened, we have a signal on the output as well. So we have the kind of the opposite logic on this side. Currently we have a signal going into the control inputs, so both inverters are closed, so we have no current going into the light bulbs. Now if we close this switch, we have control input 0, then the gates open. Since we have no current on this side, we also have no current going through the output. And since we have a current on the input here, we also have a current on the output here. This is basically how all the 5 switches work. We have an input-output connection, and we have 5 different ways to open or close the switches. So depending on what we want to do, we choose one of these 5 switches for the logic we'll do. Now with these 5 switches we can start to create some more complex logic. For example, here we have an AND logic. We want if we want to have 2 switches enable, or 2 inputs being 2 input signals, and both have to be on in order to have our light bulb being on, we can combine our switches in this way. We have the 2 wall switches. One of the wall switches go into the default input of this automatic switch. The other switch goes into the control input. And only if the control input opens the switch and there's also a current on the switch input, then we'll have a output on the switch and the light will go on. This second part here is a way to protect your logic from current flowing backwards through your construction. It basically we have this signal here, and the signal ends at the control input, and instead we just copy what is the control input into a new output that is based on the static 1 signal that we have all around here. So you can see it's all the way from the start, it's the same signal, just a static 1, and we'll use this going further all the time to protect our logic from any hazards or interference stuff and so. And I also recommend to use this gate because if we switch this gate for a inverter, we can easily change this into a NAND gate. So a NAND gate, I can show you that in a second. If we take the inverter instead of this way, so we can delete this. Now we put the inverter in instead. We can see that we have both of the signals on, and these signals will have the we'll have this gate being enabled, but because this gate is open, we close the output gate, our inverter switch, and the light bulbs are off. If we now switch any of these 2 switches, the light bulb will go on. So it's for this one, and it's of course also for this one. It works just the same, and it's also if you disable both, so the light will stay on this way. If we use this construction with the 2 switches, we have the same complexity for an AND switch and a NAND switch, for an AND gate and a NAND gate, and so they work basically the same, and it's easy to just change the logic at one point, and you don't have to rearrange all the wires to do so. Our next logic is an OR gate. We have 2 inputs again, and we want to have an output whenever at least one of these 2 inputs are on. So we can try it. We can see if we activate this the switch, the signal will go through the switch into all these wires, also back into this wire, and into this control input. The control input will open the automatic switch, and the static 1 signal is allowed to go through as an output that will light the bulb. We will have the same result if we activate both switches, or we have only the other switch activated, and we have a deactivated lamp only when both switches are deactivated. Now with this switch, it's the same we had over here with the AND gate and the NAND gate. If we switch this automatic switch for an inverter, we'll transform the OR gate into a NOR gate. This just works the same way. Our third logic gate is a NOT gate. The goal of the NOT gate is to have a single input and an output that is the opposite of the input. So if we have a signal as an input, like here, we want to have no signal as an output, and if we have no input, no signal as an input, we want to have a signal as an output. The way it works is, again, we have a static 1 going into a switch, and we have our variable input going into the control input, and since the inverter will open whenever the input is no signal, and therefore have a signal as an output, and vice versa, we have made a gate that will invert our input. And I think that's the reason why they named this an inverter, even though it doesn't actually invert anything. So the first gate is a clock signal. The goal of our clock signal is to have a signal that will alternate between on and off, so we can force our logic to work with a specific timing. So if we activate our signal, the signal will go into our inverter, because in the first step the control input of the inverter is no signal. The inverter is open, so it will allow the signal to go through the switch and then end up in the control input, where our signal closes the switch, so we have the no input anymore, therefore the signal opens again, and so forth. So this way we have a clock signal that will help us greatly in in more complex logic systems. Our last gate is the XOR gate, or you can call it an exclusive OR gate. The goal of the XOR gate is, when you have two inputs, you want the output be 1, or an active signal, only if 1 and exactly 1 of the two inputs is on. So if we activate the upper one, we want the light to go on, and if we activate the other switch as well, you want the light to go off again. Now how do we achieve this? When we have only one light on, one switch on, the signal will go into this inverter. Since the input from the other input is no signal, the inverter switch is open, and we get a signal that goes into the light. At the same time, our signal, our input here, closes the switch for our other input. So as soon as we toggle the other input, this input blocks this output. So even though we have a signal here going into the inverter, we have no output, and but this switch also now starts to block the other output. So even though we have a signal here going into this inverter, because it's the inverter is closed through the other input, we have no output here, and the light stays off. So yeah, so there we have it. These are our 5 logic contraptions, the basic building blocks of everything that we can do with the logic in No Man's Sky. It's basically very close to everything you have in real life, and I'm quite amazed that they did this logic so well. I hope they will make these switches, these ticks, a bit faster, because this clock here ticks about has a frequency of about half a hertz, and if you want to do some serious logic, you will slow it down to a sixth of a hertz, and yeah, it would be a bit better if we had about maybe 3 or 4 hertz for our logic contraptions, so the electricity can actually calculate something without taking an infinite amount of time for it. So yeah, there we have it. I hope you liked this little tutorial, this little tour through the No Man's Sky logic. If you liked it, please comment, tell me if you have any questions about the logic. I'm happy to explain everything and answer any questions, or answer all the questions actually. And yeah, and if you liked it, I'm looking forward to making another video about the more complex logics with that you can build with all this logic stuff. Yeah, so I hope you liked it, and see you next time.